Okay, so with some delay, welcome to our talk on monitoring Kubernetes clusters with Prometheus. This is Bjorn. He is my former colleague from SoundCloud, and he still is working there. We were together in the production engineering team, where Prometheus was essentially born, in a way. I joined CoreOS a couple of weeks ago, where we are now building out a monitoring team around Prometheus. And we will basically now go along the journey of SoundCloud's infrastructure, which shifted from a previous solution to Kubernetes and Prometheus. Before we start, we have an announcement to make, and you might have heard it already. But for the past year, Prometheus grew incredibly, like way beyond what we ever expected. And to sort of keep ourselves focused on the development of the project, we were looking for a governance structure to basically put the project into. So we are now happy to announce that as of yesterday, we officially joined the Cloud Native Computing Foundation, where we are the second project after Kubernetes. So we are in good company, and we hope this will go really well in the future. And now Bjorn will go on and tell you about the architecture of SoundCloud in 2012.
Yeah. Hello, is it working? Okay. So 2012, a long time ago, we are kind of going back to the origins here to tell you the love story, why, how Kubernetes and Prometheus became best friends forever. So 2012, obviously no Prometheus, no Kubernetes, and SoundCloud was still running on a Ruby on Rails monolith, which is like the normal thing you do as a startup, right? You want to get something going quickly, you want to iterate quickly, so yeah, Ruby on Rails, there you are. In the unlikely case that you're actually successful, you are in trouble, however, because Ruby on Rails has many problems with like large-scale problems, with large-scale installations. So in 2012, SoundCloud was popular enough so that we ran into a lot of problems, scalability in terms of resources, also like nobody dared to touch the monolith. We called it the mothership because it was so complex that nobody iterated quickly on it. Next slide, please. So we had to drop the microservice bomb. Perhaps I should stand here. So microservice is the solution for everything, right? I mean, usually it's more like the source of more and new problems, but it could also help you if you do it the right way. So SoundCloud became some kind of poster child for microservice migration, and a lot has been told about microservice migration at SoundCloud. I won't repeat that. This is only about 2 operational issues, and the first of it is, how do you even run microservices? Probably everybody screams, yeah, use some cloud platform provider, which is fine, but if you don't want to log into a single cloud platform provider, or you even want to run on bare metal like SoundCloud, then you cannot just use a cloud platform provider. You need something to run all those microservice instances, and the buzzword would be containers or something, right? So in 2012, nobody was really, only the cool kids would run containers. Or it wasn't even cool to run containers. It was a hipster thing before it was cool. No Docker in 2012, so containers were really hard, but some people like Google ran containers and SoundCloud ran containers. So we had our own solution for that, because containers alone and even Docker alone doesn't do everything. You still need a system that turns up and turns down containers. That's called orchestration. So what we did, we built an in-house Heroku-style platform as a service system called Bazooka, and that would run containers. And we could run microservices in containers, pretty good. One limitation was it only runs 12-factor apps because it's modeled after Heroku, which is for 12-factor apps. If you don't know what that is, look it up, 12factor.net. Oops. Funny. It's like analog broadcasting or something. Anyway, I keep talking. There we are. It's back. It's pretty good fit for microservices, but sometimes you want to run non-12-factor apps that are stateful or something. So that wasn't possible with Bazooka, and it had a number of other problems, like less resource isolation than you could have with containers. No sidecars, which is probably something you know, because you all like Kubernetes fans. So sometimes you want to run multiple containers on the same machine, and they should share some parts of the namespace. That just wasn't possible with Bazooka, and there were a lot of maturity and like fundamental design problems because it was a first system, like it was pretty innovative at its time. So we had to do something else. In the meantime, like all those years passed by, and in the open source world, something has happened, and some people implemented more mature systems, like second systems, and as you could guess, what we came up with in the end, after careful consideration, was Kubernetes. Now, it would mean carrying coals to Newcastle if I told you about Kubernetes at this conference, but there are two things that Fabian will tell you that are important in the relationship with Prometheus.
So after deciding for Kubernetes, basically Kubernetes came from Google initially, right? And so it was built on 15 years sort of experience in cluster management. It also has a lot of heritage shared with Google's internal system Borg, but it also has conceptual differences. And this is, as we will see later, quite a parallelism to Prometheus. Since you've already heard all the things about Kubernetes so far, I guess, we'll just talk about one very simple concept Kubernetes has, and that's labels. So in Kubernetes, you have sorts of different entities, right? You have a service, you have a pod, you have a node, and everything you have as an entity, you can basically attach labels to, and labels are just simple key-value string pairs. And this is really powerful because it allows you to describe all your entities in a very complex way and in a way you want to describe it as the operator of the cluster. What makes labels so powerful is that labels are also used to identify entities. So if you want to define relationships, most commonly in the case of having a service, and a service is just an abstract object, right? A service is nothing if you don't have some pod behind it which actually implements the API contract serving the service. So how do you define the relationship that a certain pod belongs to the service? And to do that by just selecting all the pods by certain labels. So you don't have a strict rigid tree hierarchy which defines this pod as part of the service. You just tell your service all pods that have this certain label, in this case here app equals my API, belong to you. And then basically all the requests that are directed at the service are routed to all the pods that satisfy these label requirements. So this is like a really powerful way to define really flexible relationships. And as we will see later, labels will be a really important thing as we go to Prometheus. And now Bjorn will tell you about monitoring at SoundCloud in 2012.
So yeah, back to 2012. So we were going microservice, and I promised two operational concerns. The one was how to run that, and the other is how do you monitor that. And 2012 was the year of #monitoring sucks. So open source monitoring world was in a sorry state. There was a new kid on the block, Statsd, which we tried out. So originally we had Nagios like everybody else, and probably most of you still have Nagios somewhere. It still sits in a corner, a bit grumpy at SoundCloud. So Nagios is traditional host-based black box monitoring, and it does that quite well, but it's totally not a fit for like a service-oriented world, especially for microservices, for various reasons. Statsd came out in 2011. We tried it. It's kind of more service-oriented, does a lot of things right, and solved like a third of the problems we had, but there were still another 2/3. So we used Statsd to feed into Graphite. Yeah, okay, but there were still problems. What are actually the challenges of monitoring your microservice architecture? So why are you going microservice? Because you have scalability problems, you have a lot of traffic. So there's a lot of traffic to monitor, and you actually expect that to grow. This is why you build an architecture that is able to grow. So any monitoring solution where your monitoring traffic grows proportionally with your user traffic has already kind of a problem. And if you know Statsd, it does that, right? For every query you monitor, it sends a UDP packet, which is not only proportional to user traffic, it's also UDP. So it probably falls over in the moment you need it most dearly if you have a problem in your network. So kind of in hindsight, bad idea. Then you also have more targets to monitor. Not only that you scale up, you have like 1,000 hosts or something, you also have a lot of containers on your hosts. Those hosts become bigger and bigger, so they run more and more containers. And microservices are called micro because you can run many of them. So you have lots of small containers on a large number of hosts, and it's all pretty complicated and a lot of stuff to monitor. So this all it's already difficult enough, but then all those targets constantly change because in the modern world, you don't statically put Apache web server on some host, and if you update it, you update the software, and then you restart it, have a tiny downtime, but everything is as before. No, in the modern world, you scale up a new version of the software on other nodes, and you can canary it, and if it works, you scale it up even more, and you scale down the old version, and if one of your nodes falls over, you do the same with to replace the instances. So it's a moving target, a lot of targets, and they also move. Why is that a problem? It's a problem if your monitoring system tries to accomplish both of the following two things, which is first of all a fleet-wide view. So of course you want a fleet-wide 99th percentile of your servers, but you also want to drill down into individual instances. Like let's say your 99th percentile latency is not good enough. Is it a problem with my canary instance? Is it a problem with a single instance with broken hardware, or is it a general problem? So to have both of that in the same monitoring system and combined with all the other problems, kind of nothing worked. Finally, this is the most important thing actually, meaningful alerting. Traditional world, if your host is down, you page somebody and somebody has to wake up and take care of it. In the modern world, thousands of hosts, I don't know, 10,000 of containers or something, always something falls over, but your system is able to cope with that. There's no reason to wake somebody up, otherwise you would wake somebody up all the time. So your monitoring system should actually take that into account and should alert you if the users are impacted or if the users are about to be impacted, but not if something is wrong in the system, but your design can cope with it. That's called symptom-based alerting. There's a little write-up by a former colleague of mine, Rob Evershoek. There's also a book now out there, we'll talk about that later, that also tells you something about it. And yeah, all of that should be possible with your monitoring system. You have to monitor everything. I mean, there's still, even in the service world, even in the cloud, there's still hosts, there's still a network, it still has to be monitored. Then you have containers as the new thing. You still have applications, just way more of them. And then there's another thing that is added to the mix, which is the orchestration system. So loads of stuff to monitor. Ideally, you don't want to have different semantics for each of those. Ideally, it's all the same monitoring system, including your alerting. Spoiler alert, here on the right, grayed out, this is how you get it all into Prometheus, which is obviously the solution to all our problems with everything forever, says Benjamin Stafford from Fitbit. I don't know why there's a question mark, because it's obvious, as he said, right? So this is how Prometheus happened. We were there, we tried all the new stuff, like StatsD, and it still didn't work. And then Julius, who's in the audience, and Matt Proud, they were engineers at SoundCloud at that time. They were both former Googlers. They knew how, Google, they ran into the problems 10 years before everybody else. So they knew how they did it. So they wanted something similar. They missed it. So they tried an experiment in their living room. And they implemented something that had semantical similarities to what Google did. And it kind of worked. And they convinced their superiors at SoundCloud, let's just invest in that. Let's develop a brand new monitoring system. Open source, of course, because SoundCloud does everything open source. That's not audio core business. So it happened and became reality. Initially developed at SoundCloud, open source from the beginning. So even in 2012, if you knew where to look, you could see it, but nobody saw it. It was clandestine, I don't know what. In 2015, we thought it's mature enough to make noise about it, and then we thought 5 people will understand what we're even doing and they will like it. But the feedback was overwhelming, and now you see, a year later, CNCF together with Kubernetes, so worked kind of well. So, inspired by Google's Bog1, but not Bog1, significant differences, but yeah, semantically similarities, similar to Kubernetes and Bog. Collects metrics at scale via HTTP. That's the first culture shock for most people. What? I need an HTTP server on every instance of a microservice? It's actually not a big problem because microservices often talk HTTP to each other. It's just another client. We have a little broadcasting problem here again. Okay. Scalability is we try to be self-sustained per node, so we don't want to depend on some distributed backend because that distributed backend is probably down when you have a problem and you need your monitoring system. So we have self-sustained individual nodes that can ingest millions of time series, thousands of targets, millions of time series. Current record is 800,000 samples per second on a single node. You can still scale that out by horizontally, vertically, or you can just do it multiple times for redundancy, and there are no external dependencies. So to cover the basis of Prometheus, because like some of you might know that already, but usually there are a lot of people in the audience that don't know that. First of all, there is this labels thing. We already talked about that. So every metric in Prometheus is labeled. So if we count HTTP requests, we call that HTTP request total in Prometheus lingo. We just not count it like company-wide or per instance. We count it per instance, per path, per status, per method, or whatever you want. This is like freely configurable. That means we have a lot of counters, like we have the number of metrics at all, then the number of possible values for the instance label, times the number of possible values for the path label, and so on. So easily you have millions of time series in your company or in a part of your company even, and that's why we made it scale to those numbers. So why is that important? Because with that many individual counters and metrics, you can actually answer a lot of questions after the fact. Example question, what are the 3 path method combinations with the highest number of failing requests? You use PromQL, our expression language, to formulate those questions, and you don't have to bake it into your setup. You can go to your Prometheus server and hack those questions in PromQL. It looks like that. Or what is the 99th percentile request latency by request path? So this is all like aggregating over your whole servers, but you could also drill down into individual pieces. Let's just look at it, how that looks like. So we look at the first query. So go from inside out. Here's our counter, and here's our status label with regular expression match. So we only want to see 500s, but all of them, 503, 500s, whatever. So match that by regular expression. Then we take a rate averaged over 5 minutes. So that gives us queries per second from a counter. Counter always goes up, so it's boring to look at. Like it's just a graph that goes up and to the right. But the rate gives us QPS. And then we sum it up by path and method. And then we get something like that. Right? I mean, this is the most current value, but Prometheus has a time series database baked in. So you can plot this over time and draw beautiful dashboards. But here we just want to know what's my busiest path method combination. And here's the answer. So, instrumentation, that's the next culture shock. So if you want to use Prometheus properly, you have to instrument your code. That's called white box monitoring. If you already use StatsD, it's not a culture shock because StatsD does exactly the same. But if not, people usually faint at that point. It's actually pretty easy. We have client libraries in like all important languages, or more or less. This is an example in Python because it's pretty simple. So you have metric types in the client library, and then they give you interesting methods for instrumentation, like the Python thing gives you a timer decorator. So the one process, the one function that processes your request, you can just decorate it, and then it will put the timing of that function into a histogram. Histogram is kind of a counter with buckets for latency ranges, and from that you can calculate quantiles and aggregatable quantiles even. This is what many monitoring systems don't get, so it's pretty nice. If you don't want to instrument your code, you can check, perhaps you're lucky enough and you are using a product that is already instrumented. So some of you might have heard about Kubernetes or etcd or something, right? They all are already instrumented with Prometheus. So they have that endpoint already, and you can just spin up Prometheus and let it scrape your etcd or your Kubernetes component. And that's why we put on this integration slide like things like Kubernetes or etcd must be some, there's etcd, right? Then sometimes you have code that is not instrumented and you are not able or willing to instrument it. Let's say your MySQL database. That's still not a problem because MySQL has some metrics, like MySQL has like stats tables you can look at. So we wrote a little binary and we called it a exporter, MySQL exporter, that logs into MySQL, checks out those tables and exports those metrics in the way Prometheus likes it. So you scrape that binary, it exposes Prometheus metrics based on the metrics in MySQL. And we have those exporters for like 100 other systems. This is actually not up to date. There should be way more little icons here. I have seen this with like commercial monitoring systems, like hosted commercial providers. They have a lot of integrations and they show off with all the integrations. So we thought we should have something like that as well. It's pretty colorful. And like with Minecraft, we knew like we're now mainstream. Okay. Now, this is all about the love story of Kubernetes and Prometheus, right? So now how does this all combine? If we go back in time, in 2012 there was no Kubernetes, but we developed Prometheus and it kind of fits well with Kubernetes. How was that even possible? And the other way around is also true. Like when the Google engineers developed Kubernetes, they had no idea there's Prometheus. They could have had an idea, but they didn't, right? So still, it fits quite well. Why is that? I always tell people there is something, like some secret sauce, like a mindset, how you run large-scale production systems in like the Google way. Giphy wasn't even a thing, right? But now there's a book. So I'm totally biased because because I know like all the people who wrote that book, and Niall Murphy, one of the like main authors, was my former boss. But you should trust me. You should buy this book and read it. This tells you way more than just monitoring and cluster management and everything, but you see what's the mindset, and you can't guess why like Prometheus and Kubernetes play well together. Let's come to like a narrow scope. What is actually the what is more concretely, how do you integrate Prometheus and Kubernetes? And this is basically along 3 questions. The one thing is, I run a service in Kubernetes, how do I monitor it with Prometheus? Obviously, right? But I told you on that other slide, you also want to monitor your orchestration system. So how do I monitor Kubernetes with Prometheus? And then we want to like make the cycle complete. How do I run Prometheus on Kubernetes? And Fabian will answer all those questions.
So starting out with how do I monitor my services running in Kubernetes? So here we have a Kubernetes cluster in some production namespace, and we have a service running, right? So what do we want to know now? Essentially, we have all these pods, and ideally, we want to monitor every individual pod. And what's important here is in Kubernetes that containers come and go, and they can come and go really quickly, right? It can be like 5 or 10 minutes even. So what your monitoring system should be able to do is to pick up these changes really quickly, and as a pod comes, it should be able to monitor it right away, and as it goes, it should stop doing that. So that's why Prometheus natively supports service discovery with Kubernetes. So Prometheus talks to the API and gets a set of all your pods, and then places a watch on the API, and this way it updates the set constantly. So as soon as you scale your Kubernetes pods, Prometheus will pick it up and start and stop monitoring them. So it then monitors all these pods, right? So and we get also what we get as a piece of information is basically for each pod the pod IP. So in the end we have all these time series per pod, so we can actually drill down into individual pods in hindsight, which is really good. But there's actually more information here, right? So we have a namespace, for example, and the service name, which is pretty obvious. But all the pods also have labels, and the service can also have labels. And it would be pretty great if we could take all these labels, right, and take them directly into our metrics, so that we could afterwards tell, okay, I have obviously 2 groups of pods running here for the same service, and they're running different version, because I set this version label to these pods. So I can later on aggregate, is this version, does it have a higher request latency than the former one, so do I have a regression? Or did the performance improvement I tried to implement actually work? So with Prometheus, that's possible, right? We talk to the API, we get all the labels, and we attach them directly to the time series we get from these pods. So we can afterwards aggregate along all these labels you have in your Kubernetes cluster. So that's pretty great. But there's actually more where Kubernetes plays really well with Prometheus. And that's what Bjorn talked about before, exporters. So let's say you're running some legacy application or just a third-party application, and these are often not instrumented with Prometheus natively, but you are still interested in having these metrics directly in your monitoring system. So that's why we have these exporters, which don't do much except for taking some sort of metrics from your system that it exposes in some way Prometheus can't understand and just translates it into metrics Prometheus can understand. And pods solve exactly this problem, right? So if you fire up a MySQL server, you can also fire up the MySQL exporter along with it, and then the MySQL exporter will get the MySQL metrics for you. And if you put them both in the same pod, Kubernetes will take care of scheduling them together for you all the time. And for Prometheus, this is a completely transparent process. So Prometheus doesn't even know there's an exporter. It doesn't even know that this application is not natively exporting anything. So again, a perfect match, basically. So that's basically covering how do we monitor services in Kubernetes, which is pretty neat. But we might also want to monitor our Kubernetes cluster itself. So there are many components, and they can go bad, right? So we want to know. So what would we have? And in the basics, Kubernetes uses etcd pretty heavily, right? So it's a pretty important component. Then we have kubelets, which are the agents running on each node belonging to your cluster. And then we have API servers. So these are the basic components, and we want to monitor them all. And we are super lucky here, because etcd is natively instrumented with Prometheus metrics, and so is the API server, and so are the kubelets. And the kubelets embed CAdvisor, which also natively exports Prometheus metrics. So we basically just configure a Prometheus server to scrape all these components for metrics on this native standard endpoint, and you're basically set and done for monitoring your cluster components. Pretty easy. So in these diagrams, we have always seen Prometheus being sort of outside of your cluster, which makes sense in many ways. If you're shifting towards Kubernetes and have an existing setup, you probably don't want to have the trouble of migrating two systems at the same time. So it's totally fair and doable. You only have to take care of Prometheus being able to route your pod IPs, and you have to do a little configuration about service discovery authentication. And then you have to have some sort of conventional deployment like Chef or Puppet. But you also can run Prometheus inside of Kubernetes. So this is also pretty simple. It actually makes configuration a tiny bit easier. And you just do it by doing kubectl run, providing an image, and suddenly you have a Prometheus pod, which can now start working. Of course, there's a bit like of boilerplate around it, so you have to basically define your configuration, and you probably want to wrap it in a service and define some resource constraints, but it basically boils down to this. And the configuration is pretty much standard, by the way. So you essentially define a configuration for your setup once, and it should work with all your services you deploy as they come and go. And then basically the diagram shifts to this, which looks pretty much the same. Nothing much changes here. And for the cluster component monitoring, yeah, also pretty much the same. So one question that remains is probably, we have local storage, right? So we are storing all this time series data somewhere persistently. So pods are not exactly long-living, and if my pod dies, my data is gone. That's pretty bad in a way. So as there's no like one unified storage solution for Kubernetes yet, what are our options? Option A is do nothing. That's actually okay, depending on what you want to do. Long-term trending, for example, how are my requests today compared to like 1 month ago? It's important, it's interesting, but it's not necessary for all parts of things your monitoring system should do for you. So what you're often interested in is like the last hour, right? So your monitoring data gets exponentially less interesting over time. And for your critical alerting, usually the window of the last 1 to 15 minutes is what the alerter needs to know. So if you fire up a new pod and just have this fresh data, it actually works for a lot of use cases. Option B is, of course, network and cloud volumes, right? So if you're on Google Cloud or in AWS, that's super easy. You just tell Kubernetes to mount one of these cloud drives into your pod, and Prometheus just writes out its metrics to these, which, of course, now puts a network link in between Prometheus and your storage. But that's actually fine, and many users are using it as well. So it's not like 100% reliable, but it works well. And option C is the most rigid one in a way. So you can actually tell Kubernetes to schedule certain pods on certain nodes. So if you just want to take your previous external setup into your cluster and tell Kubernetes to take care of scheduling your pod and restarting it if it fails, then you can actually just tell Kubernetes to always start it on the same node, and then you just mount the host volume of the original node into your container, and Prometheus then writes directly to the host disk. And then, of course, if your pod dies, you just mount back the volume and you have all your data. Yeah, and until we have found out the ultimate option for storage, this is like what you can do, and you sort of have to weigh out what's the most important for you. And yeah, over time, of course, we want to have some sort of long-term storage, right? So ideally, we can at some point be at a stage where we just have option A, and you just don't care if your pod dies, because if you start a new one, it can just go back to your distributed long-term storage and basically backfill its local version of all the time series data. And that's basically the theoretical part. Now we have a little demo, which hopefully works. So yeah, here we have a Tectonic cluster running, so Kubernetes. And we see here in our production namespace, we have 4 pods of our example application running. And we have a few nodes here, which belong to our cluster. And we also have a Prometheus pod running, which is running in our default namespace. And this is the interface of this Prometheus server. So this is basically the status page, which just shows you the configuration and basically what am I monitoring right now and is the monitoring currently succeeding. So here, for example, we are monitoring our one node etcd setup. We are monitoring various parts of the example application. We are monitoring the API server, and we are monitoring the kubelets. And just to show you, this roughly looks like this. So that's basically what the metrics endpoint that exposes your metrics look like. It's just a text, basically a text of that defines all your metrics and all your time series and the current value it has. And as we can see, there are a lot of them for all your containers and all the stuff. But the interesting bit here is, of course, the example applications. So here we see, for example, that we are actually importing the namespace information directly into Prometheus. And we can distinguish between the namespace development and the namespace production. And this label is also available in all our metrics. So this application, for example, exposes a metric which is called CodeLab API request duration seconds bucket, which is just the bucket. These are the buckets of histograms for the request latency of the service at certain endpoints. And here we can see a simple, relatively simple query to get the 95th percentile of this metric. And in this case, this metric has certain labels attached, right? Like the status code of the HTTP request, the request method, the request path, and we decide to aggregate these away to just don't have like 500 lines here. And what we end up with are these different graphs here, and they are all annotated with the labels that belong to it. So here we see, for example, the instance. So for each line here, we know from which pod it comes. We know the namespace in which this pod is. And for example, we have added the label type frontend here in Kubernetes, which we also see in our metrics. So you could, for example, aggregate across all your front ends and see the average latency for all your front ends. And the important thing here is that we can now play with all these labels, right? We can aggregate the namespace away, for example, which takes a bit if your Prometheus is a pod on a 5-node VM setup. So this doesn't look much different, right? But let's say now we want to aggregate the individual pod and just want to aggregate basically across all our entire namespace. We see that the curves can look pretty different, right? I mean, depending on the angle you look at this thing, you get very different graphs, which basically shows the importance of being able to do this after the fact, right? This looks completely different from what we've seen before. And we can now investigate, for example, per request path, how the latency behaves to figure out like a certain endpoint is only misbehaving. So this is just for the querying part, why it's interesting to have all these labels available to aggregate over at read time. And now the part where it gets tricky. So let's hope it works. Let's say we want to scale our application now. So in our production namespace right now, we have 4 pods running. And let's say we want to scale this down to like 1. In Tectonic, we see like pods disappearing now. And this should be picked up by Prometheus, right? And it is. Like before we had 6 targets, now we have 3, so yay. So pods disappearing is easier, right? Because you just stop monitoring something. Starting to monitor it is a bit trickier. So let's just scale this thing up to 6 replicas. And then we see in Tectonic they appear, and they're still pending, right? So we can't monitor them yet. But as soon as they're all there, Prometheus should pick them up. And there we go. So Prometheus basically just right away realizes what changes in your cluster and starts monitoring it for you. No configuration required. works basically all out of the box. Yeah, and that's basically the demo. And we are done with the talk for this part, I guess. So the only thing missing is, I told you before, we are now building a Prometheus monitoring team at CoreOS here in Berlin. So if you're interested in joining, just approach us afterwards. Or if you're interested in joining CoreOS in general, in New York, in San Francisco, there's coreos.com careers. Just apply. And also, announcement, if you haven't seen it yet, we have a Prometheus conference in August. So if you can make it, August 25th to 26th, see you there. And now we have 3 minutes for questions. Hmm? Oh, sorry, Berlin, yeah. Here.
How could you ask that?
It's everywhere, like.
So maybe we could just have a couple of minutes if anyone has any big questions, and then I just don't want to take too long since we're running a little over, so I'll ask you to take any longer-winded questions. Maybe you can just follow up directly with these two. But does anyone have any questions they would like to ask now? Yes.
Hey, how are these exporters, like the MySQL exporter, picked up? Do you use a special label for that and say this is an exporter, please also monitor that?
That's completely transparent, basically, right? You tell your Kubernetes, for example, to just co-schedule an exporter along with the application, and then Prometheus just grabs this exporter instead of the application.
Okay,
so
but how does Prometheus find out about the exporter? Is it through the API, or is it a convention?
I mean, the exporter is running in the pod, right? So it's just discovered as any other pod. So it's basically the same as a native application. Okay. There's like nothing special at all. That's the basically interesting part about it.
Hopefully a quick question. You mentioned monitoring. What about alerting?
Yeah, alerting was like not in the scope of this talk, right? It was quite compact already. We have an alert manager, how Prometheus does alerting is basically you define alerting rules in Prometheus, and the Prometheus server holding the time series constantly evaluates these alerts, and as soon as they fire, they are dispatched to an alert manager, which then cares about deduplicating these alerts, grouping them into notifications, compact ones, and then dispatching these over various integrations like PagerDuty, Slack, email, whatever you like.
Maybe one more question we have? Yes.
I can talk?
Yeah, you can just yell it out and then you can repeat the question.
Yeah.
Does it make sense to use Prometheus maybe for logging and request tracing?
So the question is, does it make sense to use Prometheus for logging and request tracing? No. No, it's just not in the scope. It's a very different approach. And to make monitoring really efficient and performant, we just can't take care of logging as well.
That's really an FAQ. Like it always comes up, and people try to use they try to use logging systems for like monitoring where they should use metrics and vice versa. And like you can Google for it. Like a number of people have written about that. And there's a nice on the Raintank tech blog. Like Brian Brazel wrote a really nice compact blog post about so what's logging good for, what's metrics good for, and it's not either or. It's really like you want both. You just want to use each for the right approach.
Okay, we're going to wrap up. If you have any more questions, you can just follow up with Fabian or Bjorn. Thanks.